Welcome back. Today I will discuss what is the continuous function on a metric space. We all of us know continuous function in a real variable. But what is difference of continuous function between real line and metric space? Today's goal of this lecture is this. At first, say what is the continuity in real line. Then I will see what is the difference between continuity in real line and higher dimension. First, just recall what is the continuous function in real variable. For this, consider a non-empty set A which is subset of R, and consider a function which is defined from A to R, and fixed a point x0 which belongs to A. Then f is continuous at the point x0 means if for each epsilon greater than 0 there exists delta greater than 0 such that x belongs to A, absolute value of x minus x0 less than delta imply absolute value of fx minus fx0 less than epsilon, and absolute value of x minus x0 less than delta means x lies between x0 minus delta to x0 plus delta, and absolute value of fx minus fx0 less than epsilon means fx lies between fx0 minus epsilon to fx0 plus epsilon, and x lies between in this delta neighborhood means, see the picture, this is x0, this is x0 minus delta, this is x0 plus delta. X lies between in this neighborhood. Consider x belongs to U, where U is this set. X belongs to x0 minus delta comma x0 plus delta section the set A, and consider this set is capital U. Then that imply fx belongs to the set V, where V equal to fx0 minus epsilon to fx0 plus epsilon. In metric space, this definition is such type. Consider a function f which is defined from the set m1 row to m2 row, which be a function. Then the function f is continuous at the point A. Here this is the row 1 metric space and this is the row 2 metric space. So, given epsilon greater than 0, there exists delta greater than 0 such that row 2 fx comma f of A less than epsilon imply row 1 x comma A less than delta. That means x goes to A. Consider x goes to A. The image of x is fx and image of A is f of A. Fx goes to f of A means this point. X goes to A means x lies in delta neighborhood. This is and fx goes to A means f of A means fx lies in this epsilon neighborhood. And in metric space, this is look like the ball. That means fx belongs to f of A comma epsilon if x belongs to b of A comma delta. Okay, and the picture is such type. Here the metric space m1 ray 1, this is the function which map m2 row 2. That means actually entire open ball b of A delta is mapped f into the open ball b of f of A comma epsilon. Okay, I hope my all viewers have understood this picture easily. What is the continuity in metric space? Similar definition, continuity in metric space is, now I will say for continuity, similar equivalent in definition in metric space. For this, consider two set xy be a set and consider one mapping F which map from x to y. Consider this is x and this is y. Consider the map F which map from x to y and consider the set B in the codomain y and A subset of x such type A equal to the set x belongs to x such that image fx belongs to B. Then what is the F inverse B? F inverse B is set of those x belongs to x such that fx belongs to B. That means F inverse of B is actually the inverse image of this B under the function f. This is the F inverse of B. Then actually x belongs to the complement of F inverse B means x belongs to capital X such that x does not belongs to F inverse B. That means x belongs to x and the image of fx does not belongs to B. That means image of fx does not belongs to B means actually fx belongs to the B complement means y minus B. That imply x does not belongs to F inverse y complement B. Okay, come back our original discussion. I will see what is the definition of continuity in metric space. This equivalent definition, from this expression we can tell another definition of metric space is such type f be a function from m1 row 1 to m2 row 2 where row 1 be the one matrix space and row 2 be the another matrix space be a function. F is continuous on m1 if F inverse B open in M1 for all open set B in M2 and B equal to those X in M1 such that image of those X is belongs to M2. This is actually F inverse B. And the actual definition of continuity is every open set in the metric space M2 their inverse image always belongs to in M1. Similar definition of continuity is for all closed set L which contain in M2 in the metric space M2 the inverse image of L is also closed in the metric space M1. That means inverse image of closed set if is closed, then this function is continuous. Here the idea closed has come by this concept because closed means this complement is open. If this set B is closed, then this complement y minus B would be open. Similarly, if function is continuous means if B is closed, then F inverse B also would be closed. That means their inverse image means x minus F inverse B would be open. Actually, these two concepts used in not only metric space, these two concepts is used in topological space also. Consider x and y to topological space, then a function f from x to y, where x and y be to topological space, is said to be continuous if for each open set V of y, the set F inverse B is open in X. Similar to for closed set, for each closed set V of y, the set F inverse B also closed in X, similar to open set. This is the definition of continuity in topological space. One example, First example, consider one mapping f from R2 to R. And the mapping is such type f of xy equal to x times y. Obviously, this is continuous function because first component x goes to x and second component y goes to y, and their product is also continuous. Obviously, this is continuous because this is composition of two continuous function. First components x goes to x and second components y goes to y, and their composition is xy. Since both component is continuous, so their composition also be continuous. Another method to check continuity, consider the singleton set 0. Obviously, singleton set 0 is closed in R, and consider this set is L. Then F inverse L equal to set of those xy belongs to R2 such that f of xy equal to 0. This is actually xy belongs to R2 such that xy equal to 0. And xy equal to 0 means this is in R2. This is actually axis. And axes are actually closed in R2 always. So, f of xy equal to xy continuous on R2 because I have got inverse image of closed set is closed in R2. So this function is continuous. Since these two definitions I have told you, this is actually used in topological space, also metric space. So I will see different example of continuity in different metric space, topological space, and this question is very important for basic knowledge. How continuity is used in different topological space. Let's see our first question. Consider one function which is defined from real line to real line, and the function is defined such type fx equal to 1 over x when x not equal to 0 and 0 when x equal to 0. Now I will see continuity in different topological space. First I will see continuity from usual topology to usual topology. Here S means lower limit topology to usual topology. I means indiscrete topology. Here I will see the continuity from indiscrete topology to usual topology. Then I will see continuity of this function from discrete topology to usual topology. But at first I will see what is the usual topology, lower limit topology, indiscrete topology and discrete topology. And you will understand the continuity in this topology in better way. What is the usual topology? Actually, usual topology is defined on real line, and usual topology is set of all union of collection of open set, we all of us know. And definition of usual topology is such type. A topology on real line is given by collection of intervals which look like open interval AB along the arbitrary union of such interval. Let's consider I equal to AB where AB belongs to R. Then the set where x equal to real number and tau, consider this union of open intervals is a topological space, and this type of topology is called usual topology. And this is topology because here obviously R tau is a usual topology, because topology means we all of us know if x tau be a topology, then x and phi always be the member of tau, intersection be the member of tau, and union be the member of tau, and all property here satisfied in usual topology. So this is the topology. That means all collection of interval, union of all collection of interval is called usual topological space in R. This is the usual topology. Now see continuity in usual topology. At first I will tell you every metric space XD actually always imply this is usual topology. Every metric space, because consider this is with the metric space XD. Here interval means, since here the metric space, here open ball means, since this is the metric space, in real number this is the interval, in R2 this is the ball, in R3 this is pair. All collection of this type of ball always be the usual metric. This is look like such type, union of such type of ball. This is always make the usual metric. And this is usual, all metric space is usual topology because empty set phi and the whole set X always are open in XD, because whole set always open in the metric space XD. And second, intersection of finite open set in XD are always open, we all of us know. And union of finite open set in XD are always open. So actually any metric space imply always this is the usual topology. So I will say continuity on the usual topology on the set -1 to 1 of the function of this function. Here the function is defined fx equal to 1 over x when x not equal to 0 and 0 x equal to 0. We all of us know a function is continuous if inverse image of open set is open. For this, consider one function which is defined from usual topology with respect to the real line to usual topology with respect to real line. And here the set, I will see the continuity -1 to 1. Consider this set is G star. Firstly, this set is open. Then to prove continuity, I will say inverse image of open set is open. Then F inverse G star equal to set containing the element x belongs to R such that fx belongs to G star, and here G star equal to -1 to 1. Then F inverse 1 comma 1 equal to F inverse -1 comma 0 union singleton set 0 union 0 comma 1. Here I have broken it at the point 0 because the function defined when x equal to 0 then value of the function is 0, and when x not equal to 0 then value of the function is 1 over x. Limit x tends to minus infinity 1 over x equal to 0. Limit x tends to minus 1 1 over x equal to minus 1, and limit x tends to 0 1 over x equal to minus infinity. F inverse -1 comma 0 equal to minus infinity to minus 1. Singleton set 0 means union 0, and 0 to 1 means 1 to infinity. Consider this set equal to G. I will see, is the set G is open in usual topology? For this, consider a function f from usual topology with respect to R to usual topology with respect to R. And in this topology, the set G is not open. Why not open? Because we all of us know 0 belongs to the member G, but for any epsilon greater than 0, 0 minus epsilon to 0 plus epsilon, which is equal to minus epsilon comma epsilon, does not belongs to the set G. Because in usual topology open set means any member X belongs to G. X minus epsilon comma X plus epsilon belongs to the set G. Here, this is the definition of open set in usual topology, we all of us know. But here, minus epsilon comma epsilon does not belongs to the set G. Notice, minus epsilon to epsilon, this is not belongs to in the set G. So, actually, this function is not continuous in the usual topology. I will see this function also not continuous in lower limit topology. At first, see what is the lower limit topology? How look like the topology? Consider the set equal to R and tau equal to collection of all half open intervals of the form. Here collection of all half open interval is look like X such that A less than equal to X less than B. From the lower limit to usual topology, the function is not continuous because define a function f from SR to UR, where SR is the lower limit topology and UR is the usual topology. In this set, from lower limit topology to usual topology, the function is not continuous. Why not continuous? Because 0 belongs to the set G, but since in lower limit topology, the set is look like such type. So, 0, 0 plus epsilon, which is equal to close 0 open epsilon, this is does not belongs to the set G. Okay? This is not belongs to the set G. So, G is not continuous in the lower limit topology. I hope my all viewers have understood this concept easily. Okay? Oh well. I will check. The function is defined from indiscrete topology to usual topology. Is the function is continuous from indiscrete topology to usual topology? At first say what is the indiscrete topology? Indiscrete topology is topology of X containing the set X and the empty set phi is called indiscrete topology. For this, consider one function f from R tau to R usual topology. Since here the tau is empty set phi and R itself, so the set G is not open in this set tau. So f is not continuous from R tau to R usual topology. Okay? What is discrete topology? Discrete topology is the topology which is consisting all subset of the set X is called discrete topology. If we consider X equal to 1, 2, 3, then this tau is actually all subset of X. So, tau is called discrete topology. That means discrete topology contains all subset of any set. I hope my all viewers have understood what is the discrete topology. But if we consider one mapping F from discrete topology to usual topology. In discrete topology, we all of us know all subset of S content. So D equal to A such that A subset of R. Then for any open set G star in the usual topology R, that imply F inverse G star is open in the discrete topology with respect to the set R, because F inverse G star contain the set minus infinity to minus 1 union 0 union 1 to infinity, and this is actually open set, open subset in the set R. So F inverse G star is open in R with discrete topology. Therefore, I have got inverse image of open set is open when mapping from discrete topology to usual topology. So F is continuous in this topology. I hope my all viewers have understood this. This function is continuous on the set -1 to 1 when function is defined from discrete topology to usual topology. I hope my all viewers have understood. Okay? Well, I will stop here. In my next video, I will discuss this type of question and this type of concept again, because this type of concept actually very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.